Hello everyone. Okay, this video I'm going to show you the deflection calculation of the beam. Okay, and the example is 16.6. Okay, he says there is a beam placed on a support, and A is a pin support, B is a roller support based on the picture. Okay, and the problem is very straightforward. Find the maximum deflection of the beam. Okay, so I don't have enough space for here for to write down my calculation, so I use the other panel. Okay, okay, here is the other panel. Okay, so he said find the maximum deflection of the beam. Okay, for such problem, actually, the first thing you want to know you want to do is find the elastic curve. Find the elastic curve. Elastic curve. Okay. Okay, if you find the elastic curve, okay, of the beam, and then you can determine the maximum deflection of the beam. Okay, so the key point is find the elastic curve. Okay, so how to find the elastic curve when we applying many load on a beam? Okay, first of all, you need to calculate the reaction force or reaction moment. Okay, that's the first thing you have to do. Okay, and I say A is a roller support. A is a roller support, and sorry, A is a pin support, and B is a roller support. So let's write down a free body diagram. Okay, let's write down free body diagram. I just regarded the beam as a straight line. Okay, a straight line. Okay, and the position A, because A is a pin support, so I have a reaction force like this, right? AY and AX. Okay, because A is a pin support, and B is a roller support, and roller support we only have the upward force, right? Okay, so first of all, we need to solve the AX, AY, and BY. Okay, and how to solve the AX, AY, and BY? Okay, you use the rigid body equilibrium. Okay, rigid body equilibrium. Rigid body equilibrium. Okay, first of all, rigid body equilibrium. Rigid body equilibrium. Okay, and then when you do the rigid body equilibrium analysis, we need to draw the free body diagram. Okay, the free body diagram is here, but right now it's not that complete. Okay, I forget the force here. Okay, write down the force acting on this object and free surrounding. Okay, so here is 150 kilonewton times meter, and okay, this is A, this is C. Here is B. Okay, and the distance of AC is 3 meter, and distance of AB is 6 meter. Okay. Okay, so let's use the rigid body equilibrium to find a reaction force. Okay, so the rigid body equilibrium, the condition is the resultant force at x component is 0. Okay. Okay, the resultant force are x components. So let's write down all the x components of the force in the system. Okay. X component, we think we only have this AX is X component. We only have AX in X component. Okay. So let's say AX. Yeah, that's only the X component force. Okay, 0. And the resultant force and Y component also must be 0. Okay. So let's look at, okay, what's Y component force in this system? Okay, first of all, point C, it had a concentrated loading 35 kilonewton point down. Okay, and for this calculation, I assume point up is positive and counterclockwise is positive. Okay, so what's the sign of this 35 kilonewton force? It's point down. Okay, so point down is negative. It's negative. Okay. And okay, next one, the position at A, we have the reaction for reaction for AY point up. It's a Y component, so it's point up. I assume it's point up. Okay, if you don't know its direction, just assume it's point up. Okay, so plus AY. And the next one was Y component force, and the other is BY, right? BY. Okay, okay. Oh, okay. It all becomes zero. Okay. So here we'll have the equation AY plus BY equal to 35. But this equation is not enough for us to solve the AY and BY because one equation, two unknown, is not solvable. So we need to find another condition. Okay, so the rigid body equilibrium, don't forget the total moment of the system also must be zero. Okay, the total moment of the system must be zero. Okay, and for the total moment of the system, when you're trying to calculate the moment, total moment, you need a reference point. And here, I assume the reference point at A. Okay, I assume the reference point at A. Reference point at A, the resultant moment and at the point A, okay, must be zero. Okay, so let's look at, we use A as a reference point to calculate the moment. Okay, the C, the force there is a force 35 kilonewton point down at position C. And the reference point, then the reference point is A. Okay, 35 kilonewton point down. So this force will create a moment with respect to A. Okay, so it's 35 point down and distance is 3. So reference point is here. So it's counterclockwise. Counterclockwise. And counterclockwise is positive. So it's 35 times 3. And because the force at A, because this force is at the origin, at the reference point A, so this total force won't create any moment, so we can just ignore it. And that's why I select position A as a reference point. And then there is the concentrate moment at the position B, and it's clockwise, right? Clockwise. And clockwise is negative. Okay, so clockwise is negative. Okay, okay. I think I missed one thing. Okay, here is a BY. Okay, BY is here. BY is point up. Okay, and reference point is A. Okay, so the force BY will create a moment with respect to A. Okay, so it will become a counterclockwise because its point up, reference point is here, so it will be counterclockwise. Counterclockwise. And counterclockwise is positive. Okay, so it's Vy positive Vy, and what is the moment arm or lever arm? The moment arm is here 6 times 6. Okay. So using this equation, you can find the By. Okay, the force By is equal to what's the answer? And it's 7.5. Okay, 7.5 kilo. Don't forget the unit. It's kilonewton. So and then you can solve the AY. So what's the value of AY? Okay, AY is 27.5 kilonewton. Okay. And what's its direction? Because we assume AY and BY is point up. Okay, we assume they are point up initially. Okay, and after all, I got a positive value, positive answer. So that means their direction is really point up. Okay, so I just write down this direction point up. Direction point up. Okay. So we finish solving the reaction force, reaction moment from the support. Okay, and the second step after you obtain the reaction force, okay, and then you can write down the loading function. Okay, and then represent the loading function by the discontinuity function. Okay, let us write down the loading function. Okay. Okay, and the loading function right now, the loading function I said the origin is at C. Origin at C. Origin at C position. Okay, so the origin is at position C. Write the loading function from left to the right. Okay. Okay, first of all, we have a concentrated loading at the position C, and it's pointing down. Okay, so it's negative. Okay, and what's the power for the concentrated loading if we use discontinued function? It's -1, right? So discontinued function x minus 0. Okay, and it's -1. Okay, the next one is we have a force AY. We have AY point up at position A. Okay, so position is point up, so it's 27.5, and it's also a concentrated loading and start and at the position x equal to 3, so x minus 3, and yeah, it's also a -1. Okay, and finally we have another reaction force here. By is pointing up, and also the concentrated moment at position B. But position B is at the end of the end. This is the end. Okay, this is the end of the coordinate system. Okay, because we origin set as C, so the position B is the end point in this coordinate system. And and in previous video or slide, I would say you can ignore everything. You can ignore everything at the end. Okay, also there's a reaction force or moment at the end position, but you can ignore them. Okay, that that will make your life easier. Yeah, you can just ignore the end. Okay, I think I explained this before. Okay, so just so the loading function represented by the discontinued function. Yeah, the answer is just that, just so simple. Okay. Okay, so next thing is if you have loading function, then the next thing is you have to integration twice to get the moment function, right? Okay, so let's do the integration. So integration once you obtain a shear force function, okay, and then here you have to use the integration rule for discontinuity function. Here the power of the discontinued function both is -1. Okay, for the minus power is -1 and -2. Just add 1 to the power, right? Just add 1 to the power, so it will become x minus 0 power 0 plus 27.5 x minus 3, okay, power 0. Okay, that's the shear force function. And then do it again, want integration it again, you get the moment function. Okay, for the moment function, the power is the power for the discontinuity function is 0, 0. So just a typical integration rule. Okay, so it's also very simple. Okay, x minus 0, 1 plus 27.5 x minus 3 plus 1. Okay, so we got the moment function. Okay, and when you have a moment function, we can use this to solve the elastic curve by a differential equation. Okay, do you still remember the differential equation? EI times the second derivative of the elastic curve equal to mx, right? Okay, so let's write down the differential equation. Okay. Okay, so let's write down the differential equation. It's E, the second derivative of the displacement of elastic curve equal to minus 35 x minus 0.1 plus, okay, was 1 for that. Okay, and then you have to integrate the whole differential equation twice to solve the elastic curve. Okay, mu or nu or v nu to solve the nu or mu. Okay, nu. Okay, to solve the nu, integrate the equation twice. Okay, equation twice, and integration on both sides. Okay, so integrate left hand side, you'll become EI, and then it's the first derivative of the elastic curve. Okay, so here doing the integration, look at the power of this continuity function is 1, so just typical integration rule. Okay, so you will become 35 x minus 0 power 2 plus 27.5 x minus 3 power 8 power 2. And last time I said when you do the integration of differential equation, you need to consider the undetermined constant. So you need to add the C1 here. Okay, add the C1 here and the C1 here. Okay, that's undetermined constant when you do the integration. And for the integration from loading function to moment function, you don't have to consider the integrate function because you already solved the determined constant. Yeah, I explained it in the last video. Okay, you already solve the undetermined constant here, so you don't have to consider the undetermined constant in this process. But here you have to consider undetermined constant here. Okay. And then we integration it one more time. We integrate it one more time. So integrate one more time. You will have okay, just EI mu. Okay, the integration one more time. So you will have 6 minus 35 x minus 3 power 3 plus 627.5 x minus 3 power 3. And plus here C1 integration 1 will become x and plus in another indeterminate constant C2. Okay, and then we'll have solve the undetermined constant C1 and C2. And how to solve this C1 and C2? Use the boundary condition. Okay, and in the PowerPoint slide and previous I show you. Okay, you can look at the PowerPoint. Okay, and the boundary condition is okay. And the displacement at the support is 0. Okay, the displacement at the support is 0. Okay, so let's move back to the picture. The displacement at these two supports is 0, and the displacement at position A and position B is 0. Displacement at position A and position B is 0. Okay, that's a typical boundary condition. Because at this support, there won't be any displacement. We want them fixed. We don't have any deflection on the support. Okay, so the boundary condition is okay. Let me write down the condition. So the boundary condition is based on the setup of the problem. The boundary condition is okay. V of nu over 3 is equal to 0, and the other is V over 9 is equal to 0. Okay, don't forget, because in this problem we set the origin origin is at C. Origin is at C. Okay, so the point A is x equal to 3. Okay, the point B is x equal to 3 plus 6 is 9. Okay, so it's nu of 3 is 0, nu of 9 is 0. Okay, okay, so we plus this boundary condition in there. So what we have EI new if I put the x equal to 3 in there. So 3 minus 0 is 3. Okay, 3 minus 0 is 3. Okay, it's 5. Okay, 3. Okay, plus. Okay, and I put x equal to 3 here. 3 minus 3 is 0, so it's really 0. So we can just ignore it. Okay, this term, and I will have 3C1. I will have 3 3C1 plus C2. Okay, because nu of 3 is 0, so that means okay, just write down the result directly. Let me see, I write down the result directly. Okay, you will have 0 equal to minus 157.5 plus 3C1 plus C2. Okay, you'll get your first equation. And another boundary condition is EI nu over 9. Okay, plus x equal to 9 here. So you will have 6 minus 35 9 power 3 plus 627.5. Okay, I plus 9 in here. So 9 minus 3 is 6. So it's 6, 3. Okay, plus, okay, 9 C1 plus C2. Okay, and here's 0. So okay, so you will have 0 equal to minus 4252.5 plus 4.58 3 times 6 power 3 plus 9C1 plus C2. Okay, so when you use these two boundary condition, you will have you can so use and you have two equation for C1 C2, so you can solve the C1 C2, right? Okay, yeah. So that's very easy OD like calculation. Okay, so just take so just try using your calculator to solve the C1 C2. Here I won't show any detail of this type of calculation. You should do it. Okay, so you will have the C1 equal to 1517.5. C2 is equal to minus 1395. Okay, so finally, what is our elastic curve? Okay, our elastic curve. Let me see. Let me see. Let me see. Okay, we need the two equations. Okay, the slope, and the slope of the elastic curve and the elastic curve. So finally, we will have like this. EI v of x is equal to uh, minus 6.35 x3 plus 27.5 x minus 3 power 3 plus 1517.5 x minus 1395. The other is because later we'll use the slope of elastic curve, so I also write down the elastic this the first derivative of elastic curve, and it's 2 minus 35 x squared plus 227.5 x minus 3 power 2. Just put your C1 C2 in there. Right? It's it's very typical. Okay. So, okay, well, after you obtain the C1, C2, okay, put the C1, C2 in there. Okay, C1 is here, put a C1 here, C1 here, put C1 here, put C2 here. Okay, you have EI. EI mean equal blah, blah, blah. EI times the first derivative of the elastic curve equal to blah, 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 blah. Okay. So, okay, so this video, I just stop video here. Okay, because we haven't solved the problem, because the problem is want us to solve the maximum deflection of the beam. Okay, right now we just obtain the elastic curve. Okay, I think I will use the next video to demonstrate how to find the maximum deflection of maximum deflection of curve, because I don't want to make the video too long. Okay, so this video I just stop here. The next video I'll solve the maximum deflection of the curve. Okay, so see you. Okay, see you. Okay, see you in next video. Bye bye. Yeah. Oh, not too bad.